So chapter 3. So chapter 1 is just the introduction about matter, measurements. Chapter 2 about atoms, molecules, and ions. So we discussed this atomic structure, and then we discussed about the periodic table, the naming, and last but not the least, the balanced chemical equation, all of which were covered in your quiz. Okay. Now for chapter 3, this is where the calculations come in. So we're going to what we could still discuss chemical formulas as we have in chapter 2, okay, and also chemical equation, but okay, we're going to include the calculations. That's why I told you last time, you have to have your calculator in this session. Okay, so we discussed about last time about the molecules, the formula. Okay, so we said the molecules are the one for the covalent compound. The formula is just for the ionic compound. So the principles of getting the molecular mass and the formula mass is just the same. You just add all the atomic masses. If you have a molecules, the atomic masses of the atoms in a given molecule, if you have the formula, okay, the atomic mass of all atoms in the formula unit. So this is, we could say, pretty straightforward. And I want my students to assure me that if there's a question like this is already, we could say, sure points. Okay, so at least you will definitely get one correct answer if you have a problem like this one. And I can assure you, in the quiz, you will have a question like this one. And remember, you already have what? The periodic table is supplied to you. So whatever you see in your chapter 2, you will also see in your chapter 3. Okay? So what we're going to do now is we're going to calculate the formula weight of the following compounds from their formula. So if you're going to look at this, this is the formula for an ionic compound. This is a molecule. So what we're going to do is we're going to compare here to determine the mass of this given formula. And all you need is the periodic table. So calcium hydroxide. So the way that I'm going to do is I just list down all the atoms there. And then what I'm going to do, I'm going to write how many atoms are there in the formula. So calcium is 1. Oxygen, we have 1 here, but the close open close parenthesis says you have to multiply it by 2. So you have 2. And then the hydrogen, you also have 2. And the next thing that you're going to do is you need to get your periodic table because that's where the respective atomic mass is. I can put here 40.08, 32.00, and 1.08. And then you're going to put this one, 40.08, this is 64, and this is 2.016. Now, here, the unit that we have is still AMU. That is your atomic mass unit. Okay, in the molecular formula and the formula, the molecular mass and the formula mass, the unit that you have is AMU. Okay, it's not gram per mole. Later on, you will know when you're going to use the gram. So all you need to do is bring down everything here. So maybe you have what, 74.096, or you could just say this is what, 74.0 AMU. So do you think you can solve problem like this? Because the chapter 3 is, we could say, calculation question. I think I just only have, if I'm not mistaken, 3 or 4 that is some sort of non-calculation problem. Almost all the problems that we have here is calculation. That's why we'll be given 90 minutes to do this quiz or to accomplish this. Yes, question?
Yeah, somebody asked the question in the chat. They asked why is it 32.00 instead of 16?
Oh, yeah, yeah, yeah. Very good. That's my mistake. So this is a 16 and this is a 32. And if you're going to add it, this one is still the 74 mark. So sorry for that. Thank you. It's my fault. Okay. I put the 32 right away there when it should be uh, 16 times 2, the total that you have. And as you could see, I think this is the more reasonable one. So 40 plus 32 will give you 72 plus 2. About that. Thank you for the correction. Okay. Now for the other one, so this is methylamine. So all you need to do, line them up again. So you have 1. Hydrogen is 3 plus 2. That's 5. Okay. And then nitrogen is 1. So if you're going to look at this, so this is 12.01, 14.01 for nitrogen, and 1.008. So if you're going to look at this, 12.01, and then 5.040, and then you have 14.01. And then you add them together, you end up with this. So you have 31.06 AMU as the formula weight of the given substance. Okay. Now, why do you need to get this what we call formula weight? Okay, because it's central to the concept that you're going to learn here. Okay, this is the so-called mole concept. So there are 3 ways to express, okay, the amount of matter. One is in terms of mass, one is in terms of mole, and the other is in terms of number of particles. Okay. Now, the central idea here is the mole. Now, what is this definition of mole? So whenever we have a mole, this is a quantity of a given amount of substance that contains as many molecules or formula units as the number of atoms in exactly 12 gram carbon 12. So what does it mean? So when you're talking about 1 mole, okay, in a carbon 12, its equivalent mass is 12 gram. When you're talking about mole, in terms of the number of atoms, it is equivalent to a certain number. So try to imagine mole like, let's say, a dozen. What comes to your mind if you are given the word dozen? Anyone? You can type in the chat. What comes in your mind when you're given, let's say, a dozen? Okay, it's always the number what? 12. Okay, so the same thing with the mole. So when you are asked 1 mole, what is equivalent of 1 mole in mass? So the equivalent of 1 mole is in mass is equals to the formula weight of a given substance. Okay. So when you are asked 1 mole, so that means that item contains whatever is the uh, atomic mass or formula mass or molecular mass of a given substance. So if you have 1 mole of carbon, so that is equivalent to 12 grams of carbon. Now, in addition to that, you can also determine how much particle or how many particles do you have in 1 mole of substance. Okay, since the mole concept was studied by Amadeo Avogadro, they honored him, okay, the number that is related to 1 mole, and that number is this one. So that's the number of atom in exactly 12 grams of carbon 12. So when you have 1 mole of carbon, so that means you also contain 6.022 times 10 to the 23 carbon atoms. So if that's the case, so you have your mole, you have your mass, you have your number of particles. So you can just go from one expression to the other. Okay. So from mass going to mole, you could just say you divide it with the given molecular mass, or we could say now the molar mass. So how is molar mass differed from formula mass and molecular mass? Usually the unit, you use grams per mole. But if you're going to look at the number, they're just the same as molecular mass and formula mass. The only difference, if you have formula mass or molecular mass, you use AMU. But if it's molar mass, because it refers to the mass of 1 mole, or the mass in terms of mole. Okay? So if you're given the mole and you want to determine the mass, all you need to do is multiply it with the given molar mass. And if you're given the mole, okay, you are asked to determine the number of particles, all you need is to multiply it with Avogadro's number. And if you're given the number of particles, you are asked for the number of moles, you're just going to divide it with Avogadro's number. And definitely, this will be an important concept that you need to know in this course. Okay, if you're not able to get the number of moles in a given mass or a given number of what we call the particles, you don't have the right to pass the course. Okay, so when we're talking about particles, it can be atom, it can be molecule, it can be ions. Okay, so let's try to solve. I think I have several problems here for the next successive slide. And it's all about coming from one expression to the other. Okay, so the first thing that we have here is what is the mass in grams of what is the mass in grams of the nitric acid molecule? So if you're going to look at the concept here, you need to determine what is the weight of 1 molecule of nitric acid. So what are we going to do first? So maybe we can determine what's the molar mass of that one. So in some instances, they're given, in some instances, they're not. So if they're not given, you have to calculate it. Okay? So the mass or the molar mass of your nitric acid, if you're going to look this, so this is 1, this is 1, this is 3, so this is 16, this is 14.01, and this is 1.008. Is right? So if you're going to look at here, oops, I think 14 plus 62, oh no, 1.008, that's 1, that's 0.018. My eyesight is just giving away. So 14 plus 1, that's 15, so this is 63.018, or I can just put this as 63.02 grams per mole. Are we done here? The answer is no, because we need to get the grams per molecule. So you have the starting point here, and you need to go to that unit. So what's the pathway that we can get? So you could say here 63.9 grams per 1 mole. Okay, and you need to go to this one. So what equivalent or expression can you go there? So maybe, okay, the way that you're going to go here is for every 1 mole, how many molecules do you have? You're going to use the Avogadro's number. And if you're going to do that, you cancel the moles there and you end up with the unit that you're looking for. Just what we call use the number that you have. So if you're going to get the value there, so 63.02 divided by 6.02 to exponent 23. So you will get around 1.046 grams. Oh, wait, it's not just 1.046 times 10 to the negative 22 grams per molecule. Check. So question. So the very important thing is just setting up what is given, okay? What is the one that you need, and how are you going to get from the given unit to the unit that you're looking for? You need to have a lot of practice on this. That's why maybe later on we'll talk about maybe it's up to you if you want the changes. Okay. So as I've mentioned to you, the molar mass is just the mass of 1 mole of substance. And if you have carbon 12, okay, carbon 12 has a molar mass of what we call 12 grams or 12 grams per 1 mole. So let's go on this one. A sample of nitric acid contains 0.253 moles of nitric acid. So what's the molar mass of nitric acid that we have here? So 63.02. So we're going to use that. So if you're going to look at this, the given is 0.253 moles. And the one that is being asked is, what's the equivalent mass of that? And if you're going to look at the hierarchy or the relationship that they have there, where are you? What is your starting point? Okay, your starting point is this one, and you are asked to go here. So all you need to do is, what's the pathway from here going here? So if you have 0.253 moles, you are asked, what is equivalent in grams? So all you need is you multiply it with what? The molar mass that we have, which is 63.02. And if you're going to do this thing, you will get what? 50.9 grams. So analyze. Can you assure me that when you have a question like this, you're going to get it right? So what can make you not get the correct answer? Maybe you will not be able to get the correct molar mass. So that's the importance on why at the beginning of this chapter, we discuss about getting the formula mass or the molecular mass, because you're just getting also the molar mass on this. Analyze. Before we go with some other stuff, So this is just all calculation. And I can tell you, if you practice some problems, okay, before you take the quiz, you'll be in a much better position to get a good score in the quiz. Okay, so we have something in the chat. Okay. Okay, where did the 63.02 came from? Where did we get it? I didn't show you here, but as I've told you in a previous problem that we have, we were able to get the molar mass of your nitric acid. So 63.02 is the molar mass of your nitric acid. Okay. It's not given. So you have the periodic table, you have to do it. But I just give it to you 63.02 because we have previous problem where we get the uh, molar mass of this nitric acid. So let's go on another one. Now this time, I think it's the other way around. So in the previous problem, you're given the moles and you're asked for the mass. But this time here, you have a calcite, the mineral composed of calcium and calcium carbonate. A sample of calcite composed of pure calcium carbonate weighs 23.6 grams. How many moles of calcium carbonate is this? So this is the other way around. Okay. Now, you're given here the mass, and you are asked for the moles. So the first thing for you to do is get the molar mass. You have calcium. So you have 1, 1, 3. So you have 16. Carbon is 12.01. Calcium would be what? 40.08. 12.01. And you have 48, right? And you have it, that's 100.09. Or, yep, it's 100.09 grams per mole. So all you need to do, put here what? 23.6 grams. How are you going to go with the moles? So if you're going to have that, okay, what are we going to do? So we could just say for every 1 mole, you have 100.09 grams. So look at how I play with the number. Why did I didn't put it as 100.09 grams per mole? Because I want to cancel out the unit of gram, leaving me the unit of moles. So you have to be very careful on this one, because if you do it the other way around, what will happen? Grams times grams per moles will give you grams squared over mole, which doesn't make sense. Okay, this is the message that I'm trying to send you as early as chapter 1. That if you arrange the units that you have from the given units to the units that you're looking for, you will have no problem in calculation. Okay, so another thing that you need to know, whatever is the given number there, in terms of significant figure, usually that's the number of significant figures. This one are what? In terms of significant figures, these are exact number. And if you have an exact number, okay, the number of significant figures that you have there is infinite. So you just base it on the given number. So what did you get? So 23.6 divided by 100, that is equals to, this is again 0.236. No, not mole, gram. No, mole. That's 0.236 mole. Question? Now, chapter 3 quiz, if you understand it, you can get it perfect. If you don't understand it, then that's where the challenge comes in. All I can tell you is just practice in doing the calculation. You have the problem set, okay? You have the chapter, we could say pull question. So use it. Use it before you take the quiz, okay? So here is another problem, and this time, the one that is given is in grams, and you have to go to determine the equivalent moles. So you have leucine here, okay? The daily requirement is 2.2 grams for an adult. So what is the average daily requirements for leucine in moles? So again, what are you going to do? You have to determine the molar mass. So 6, 14, 2, 1, and then you have 14.01, 16, 1.0, if I'm not mistaken, trying to look at my notes just to make sure I do it correctly. 1.008, and this one is 12.01. So if you're going to look at this, so this is what, 6 times 5, so that is around 72.06, and then this is 14, so you have 14.112, you have 32, and this is 14.01. And what you have there overall, 132.182, or you can round it up to 132.18 grams per mole. So where are you going to use it? In converting 2.2 grams to moles. So how are you going to arrange it? Which is in the numerator and denominator? Is it grams per mole or moles per gram? Anyone?
Moles per gram.
Okay, so it is moles per gram. Because this is the thing, I can assure you, since your quiz are multiple choice, when you do the calculation, 2.2 times 132.18, there is a number in one of the choices to that answer. So if you are not careful enough, then you fall into the trap. So I would suggest you double check it, because whatever calculations that you did, I can assure you the number that come up is one of the choices. So you have to be very careful. So if you have 2.2 times 1 mole over 132.18, so you end up with what? 1.7 times 10 to the negative 2, or 0.017 moles. Analyze. So all that we have so far is the mass going to moles and vice versa. But the next problem that we have is we go with the number of particles. So all calculations that we have so far is the one-step calculation. So if it's the one-step calculation, I would suggest that these are the sure points for you. Okay. So let's go with this one. So the daily requirement of chromium in the human diet is 1.0 times 10 to the negative 6. How many atoms of chromium does this represent? So if we're going to look at the expression that we have, so you have mole, you have mass, and you have specifically number of atoms. Or the number of particles here, we're going to put it as number of atoms because that's the one that you're looking for. So if you're going to look, you start here, right? So this is the one that's given. And this is the one that is asked. So you develop away from here going to here?
Daddy, you need to get good at the stud so you can come to the school for the graduation.
Okay. So what else do we need? We need to get what's the uh, mass of chromium. So where do you get that? You're going to get it from the periodic table. So it's given as 51.996 grams per mole. So that information will come from your periodic table. So you can start here 1.0 times 10 to the negative 6 grams. And then for every 1 mole, you have 51.996 grams. And then, so we are already from here going here. For every 1 mole, you have the Avogadro's number 6.022 times 10 to 23 chromium atoms. So if you're going to look at the unit, grams over grams, moles over moles, giving you the unit of atom. Analyze. You just have to set up something. So question, what is the number that we get here if you do the operation? So I got 1.158 times 10 to the 16, which I'm going to round up to two significant figures. So if I'm going to do the operation, this is what I got. But you don't usually need to write everything. You have to follow the rules of significant figures. So question? Are we good? Still with me? So let's go to another concept. It's still the same, okay? But what we're going to talk about here is the so-called percentage composition. So when we're talking about percentage composition, this is the percentage of each atom in a given formula, okay? So all you need to do is what? Math. So unfortunately, this section has more math, and most of the student problem in chemistry is not chemistry, but math. Okay? So you have your lead chromate used as a paint pigment. So you are asked, what is the percentage composition of lead chromate? What does it mean? So you have to determine how many percent lead, how many percent chromium, and how many percent oxygen do you have in the lead chromate. So this is just doing the, we could say, molecular mass, formula mass, or molar mass determination. But once you see the contribution of each element, you divide it with the total. Okay? So PB, CRO, so you have 1, 1, 4, then this is usually 16. Chromium that we have, I think we determine it as 51.996, and then this one is 207.2. So what we do, 207.2, 51.996, and then you have here 64. And you add all of them, what do you get? 323.196, or you can round it up to 2. So what are you going to do? You divide that number in each of them. And you multiply it with 100. So if you do that, okay, you will have here 64.11%, 16.09%, and then 19.18%. Now, how will be the question that you will be asked in the quiz? Which element has the highest percentage? Or which element has the lowest percentage? So you can only answer this question if you do the calculation. So which element has the highest? So based on this, it's lead. Which element has the lowest percentage? Based on this, it's chromium. Okay? So those are the type of questions that you will be asked in percentage composition. Or you might be given other ways of what we call questioning, but still, the way to answer the question is you have to determine the percentage. Because you might ask, how many grams of lead are there in 50 grams of lead chromate? What would be your answer there if it's like this? So all you need to do is 50 grams times 64.11 divided by 100. And that gives you 50 times 11 divided by 100. So you have around what? 32.1 grams. So those are the type of question that you may be asked. And I think I have another example here. So for instance here, so this is the same question that I gave in the last way of questioning. So you have sugar, which is sucrose, that has this chemical formula. And you're asked how many grams of carbon are in 68.1 grams of sucrose. So the only way for you to answer this question is you need to get what's the percentage of carbon in a sucrose. So you do what we have done since the beginning of the chapter. So 12 times 12.8, that's 144.12. 22 times 1.008, so that's 22.176. And then 11 times 16, so that is 176. So if you're going to look at this, you have 342.296, or you can round it up to 342.30. And then what you do, you divide everything with this number. And you're going to multiply all of them with 100. The only one that is important for you here is just the carbon. Once you get the percentage of carbon, you don't need the hydrogen and oxygen percentage. So if you have the carbon, that is equals to what? You don't even need to do the percentage. You can always go with this one, 68.1 gram sucrose times the molar mass of sucrose over, for every 342.3 grams of sucrose, 144.12 grams of that is carbon. So that itself will solve the problem. You don't need to do this operation if ever. You just have some sort of a ratio and proportion that you have there. So what do you get? Anyone? Just some more question. Is it 42.1? $68.1 times 144.12 divided by 342.30. Anyone? This is what I get. 28.6724, which I can round up to how many significant figures? 1, 2, 3. So 28.7 grams of carbon. Analyze. Question? Before we go with percentage composition, using a little bit complicated problem. But the question that you have in your quiz is not as complicated as our next example. So when you're working with the so-called hydrocarbons, okay, hydrocarbons, these are just a compound that contains hydrogen and carbon. So as we could see, the percentage composition that has been doing, that's the mass percentage of each element in a compound. So during the earlier times, whenever they want to analyze hydrocarbons, the way that they analyze it is they burn it. Okay, so hydrocarbons reacting with oxygen to produce CO2 and H2O. Okay, so what they do, they determine the CO2 and H2O that are produced, and they weigh it to determine the amount of carbon and hydrogen in the original compound. So you have any hydrocarbons that you have here reacting with oxygen. So usually what you produce is CO2 and H2O. So once they be able to determine the H2 and the H2O and CO2, they correlate it, okay, and come up what is the exact composition of the hydrocarbons, okay, or the given hydrocarbon. So for instance, you have a benzene, okay, so a sample of the benzene that weigh this amount, you burn it in oxygen and you form 1156 milligram of CO2. So you are asked what is the percentage composition of benzene. So benzene is a hydrocarbon. So you are asked, okay, how many hydrogen and how many carbon do you have in a given benzene? So if you're going to analyze, you have 342 milligrams of that. You react it with oxygen. So what happened? It produced 1156. So you have a CO2 1156 milligram, and then an H2O. So how are we going to analyze this? What's the strategy that we can have in solving this problem? So before we continue, I have the slide about the strategy here. So use the mass of the carbon dioxide to find the mass of the carbon from the benzene. Okay, so maybe we do it step by step. So we're going to use the mass of the carbon dioxide to find the mass of the carbon from the benzene. So maybe we can start from here going to carbon. So you have 1156 milligram, okay, of CO2. Maybe we can convert it to what? For every 1 grams of CO2, you have 1000 milligrams of CO2. And then what we're going to do, we need to get the moles. So for every 1 moles of CO2, you have, okay, 44.01 grams of CO2. So where did I get the 44.01 grams? That's the moles of your CO2. Now, if you're going to look at here, okay, stoichiometry, it's 1:1. So you could say for every 1 mole of your CO2, it comes from 1 mole of your carbon. And then what do you do? For every 1 mole of carbon, how many grams of carbon do you have? 12.0 grams. So analyze. It's a little bit long, but that's how you get from finding the mass of the carbon in the benzene using the mass of the CO2. So the pathway that we have here is just from your CO2, we want to determine the amount of carbon in the given compound. So if you're going to look at the unit, cancel, grams cancel, moles of CO2 cancel, and moles of carbon cancel. And what's the answer that you get there? So 1156 divided by 1000 divided by 44.01 times 12.01. So I have here around 315 or 0.315 grams of carbon. 3155 grams carbon. So that is equivalent to what? 315.5 milligram. So what's the next step that we're going to do based on the strategy that we're given here? You use the mass of benzene and the mass of the carbon to find the mass of the hydrogen. So what's the given mass? 342. So you're going to subtract it with 315.5 because that's the milligram of your carbon. So this is your hydrocarbon. So the difference that you have there, that's the milligram of your hydrogen. So what do you get? 342 minus 315.5. So you have 26.5 milligram. Are we done? The answer is not, because what we did is we just find the amount of the hydrogen, the mass of the hydrogen in the given hydrocarbon. And the one that's being asked is the percentage composition. So what do we do? So the 315.5 divided by 342. So that's the percentage, or times 100%. So that's the percentage of your carbon. Now, 26.5 divided by 342 times 100, that's the percentage hydrogen. So if we're going to look at this, this is what? 92.3%, and this is 7.7%. So that's how you work if you have a hydrocarbon problems wherein you determine the carbon dioxide and water. And this could be the basis for the concept that we have next, the empirical formula. Okay. So when we're talking about empirical formula, this is the simplest formula, the formula of a substance written with the smallest integer subscript, or the smallest whole number ratio. So if you have an N2O4, the empirical formula for that is NO2. Why? Because you can divide it by 2. If you have H2O2, the empirical formula for that is HO. Okay, so how are we going to determine this empirical formula? We're going to have some problems on this after this slide. And there's a question of it in your quiz. Okay, so when you have an empirical formula problem, the first thing for you to do is assume you have 100 grams. Because what will happen, you will be given usually in terms of percentage composition. So if you have to assume 100 grams, your percentage is converted to grams. And then what you're going to do, you convert the grams to moles for each element. And then after that, that's the time you manipulate the resulting mole ratio to obtain whole numbers. So you may ask, how are we going to manipulate this mole ratio? You divide it. Usually the rule is divide it with the mole amount by the smallest mole amount. If the result is still not a whole number, so you have to multiply each mole by a factor to make it into whole number. So for example, if the decimal portion is 0.5, you can multiply it by 2. If it's 0.33 or 0.67, you can multiply it by 3. If it's a decimal portion of 0.25 or 0.75, you're going to multiply it by 4. So to give you an idea how it's being done, we're going to solve problems like this, several problems. So we can just continue with what we have stopped from the previous problem. Okay, so what does it do? Assume 100 grams. So if you have 100 grams, this becomes 92.3 grams, and this becomes 7.7 grams. And then the next step, convert grams to moles for each element. So maybe we can divide it with the respective molar mass. So this is 12.01 grams per mole, and this is 1.008 grams per mole. So if you have that, which one is canceled out? And then if you're going to look at the number that you have here, so this is equals to what? 92.3 divided by 12, so it's around 7.685 moles of carbon. And this is around 7.64 moles of hydrogen. So as you could see, they're almost close to one another. So you can just divide both of them by the lowest one. And you have your 1 and you have your 1. So the empirical formula is equals to CH. Analyze. Before we go to other, what we call problem. Question? You can type it in the chat. Now, in addition to the empirical formula, you also have this concept of molecular formula. So how is empirical formula different from molecular formula? So empirical formula, that's the simplest whole number ratio. Now, the molecular formula, okay, that's the formula of a given molecule, and it is usually a subscript, okay, or whole number multiples of the subscript of the empirical formula. So whatever is the empirical formula, you just multiply it with a number and it will give you the molecular formula. So to determine the molecular formula, you compute the empirical formula weight and then find the ratio of the molecular weight and the empirical weight, and then you multiply each subscript by the empirical formula by n. So you find the ratio of it. And again, we can continue with what we have started. Okay, what's the empirical formula of benzene? CH. Its molecular weight is 78.1 AMU. So what is its molecular formula? So the first thing that we're going to do is determine the empirical formula weight. So this is just what? C and H. So we could say 1 times 12.01, 1 times 1.008. You have 12.01, 1.008, and you have here 13.018, right? So what are we going to do with this? We can round it up to 13.02. So we can get the ratio, okay? Molecular formula weight over the empirical formula weight. So it is just 78.1 AMU over 13.02 AMU. And that is equals to what? Around 6. So that means you multiply the CH here by 6. So you end up with C6H6. Now to check if this is really C6H6, it should give you this molecular weight. Analyze. Before we solve two empirical formula and molecular formula problem. So let's go on solving this problem. So you have sodium pyrophosphate used in the detergent preparation. It's composed of 34.5% Na, 23.3% phosphorus, and 42.1% oxygen. So what is its empirical formula? First thing, assume 100 grams. So everything is converted to grams. Now, once they're in grams, you're going to convert them to moles. So you can divide them with the respective atomic mass. So this one, we could put 22.99 grams per mole of sodium. This one, you can do it with 30.97 grams per mole of phosphorus. And this one is 16.00 grams per mole. So the grams are canceled, so each of them will have moles. Excuse me. So you have 1.05 moles of Na. This one you have 0.7523 moles of phosphorus. And this one you will have 2.63 of oxygen. So you convert everything into moles. What you're going to do next, you divide it with the lowest values of the mole, which in this case is 0.7523. Okay, so you end up with what? 2, 1, and what do you get here? 2.631 divided by 0.75, that is equals to 3.5. So what do? We need to make it into a whole number. So maybe you can just multiply everything by 2, so you end up with what? Na4 P2O7. So you multiply everything by 2. Why? Because you have to make them into a whole number ratio, the simplest whole number ratio. So this is your empirical formula. Analyze. Question. So the last question for empirical formula with molecular formula is shown here in the slide. So you're given the hexamethylene, one of the material used to produce nylon. It's composed of 62.1% carbon, 13.8% hydrogen, and 24.1% nitrogen. So given the molecular weight of 116 atomic mass unit, what is its molecular formula? So the same thing that you're going to do, but with the addition of determining the molecular formula. So you determine the empirical formula and then get the empirical formula weight, and then from that you can determine the molecular formula. So it's the same thing that we have: 62.1 grams carbon, 13.8 grams hydrogen, 24.1 grams nitrogen. So you're going to always assume you have 100 grams sample. And then you divide this with 12.01 grams per mole of carbon, 1.008 grams per mole of hydrogen, and 14.01 grams per mole of nitrogen.
I want popsicle. I want popsicle.
So the grams is canceled, giving you the moles. So this one will give you what? 5.17 moles of carbon. This one will give you around 13.69 grams moles of hydrogen, and this one will give you around 1.720 moles of nitrogen. What do? We divide it with the lowest number of moles. And then you end up with what? So this is 3, this is 8, this is 1. And since you see that this is the simplest whole number ratio also, so you can say this is the empirical formula, C3H8N. So what do we do next? Get the empirical formula mass. So if you're going to do 3 times 12.01, 8 times 1.008, and then 1 times 14.01. Just wait. Sorry for that. I'm living near 3rd Avenue. Okay? So, Megan, don't. Get up there. Okay? So, if you're going to get this one, 3 times 12.01, okay, plus 8 times 1.008 times 1 times 14, so you will get here around, if I'm not mistaken, 58.1. So we get the N, molecular weight over empirical formula weight. So you have 116 divided by 58.1. So that's around 2. So you're going to multiply that one here, and you end up getting C6H16N2 as your molecular formula. Analyze. If you're still there, okay, if you have questions, let me know. And if ever you're not able to catch up, okay, this is recorded, so you can always look at it. So, to the 12 of you, I'm going to ask some poll question. Because that's the number that we get to determine the molecular formula when we divided the molecular weight with the empirical formula weight. The 58.1, that's the empirical formula weight when you add C3H8 and N, when you get the mass of this what we call empirical formula. What's the other? I expect 12 participants. So that means 1/3 of you are sleeping or away from the computer. Because I'm going to keep the setup that we have for chapter quiz, but I'm thinking of just giving both quizzes at the end of the week. Let's say Thursday and Friday. So you will have enough time to digest whatever happened on Monday and Wednesday. So based on the fall that we have here, okay, so only 1 out of 11 don't like the present setup, but 10 out of 11 are okay with the setup. I told you the main reason for this is so fast. So if it's a chapter quizzes, the chance that whatever you study, the topic that you study in each chapter will come out. Okay, there's a higher chance that it will come out compared to in an exam. Okay. And the thing that I asked you about the Thursday and the Friday, so maybe both quizzes, let's say uh, we did chapter 2 and 3 this week. So you can start, I will open the window from Thursday to Friday for both the, what we call quiz for both chapters. And I think during that time, you should have enough time to do this one. Are we okay on that? Because the thing is close. 7 out of 11 versus 4 out of 11. Okay. So that's the reason why I want to do this setup, because I saw some students who didn't take the quiz yesterday. Okay. So if I follow that the rule that we have, that should be zero, whatever that they have is zero, whatever is the total score. But I think this is just the second week, the third meeting that we have. I will allow them to do, or maybe take it tomorrow. But after, we could say next week, by next week, if you miss the thing, okay, then I'm going to give you a score of zero over whatever the score that we have. Okay, I will allow it only for this week. So everyone okay that instead of whatever we did on the Monday, you take the quiz on a Tuesday. So whatever we did on a Monday and a Wednesday, you're going to take the quiz from Thursday to Friday. Are we good on that? Can I see a, like a, what's that, a thumb in the reaction? I just want the best for you, okay? Because I want your score to be what we call better. So I'm expecting that as we go on, your score should be better. I was thinking that the chapter 3 quiz is when one of you gets 100, but fortunately somebody got 100 from the quiz yesterday. So somebody get 17 out of 17. Because the first chapter is 14, the second one is 17. So overall you have 31. items, the highest that you have there is 29. Okay? So to the one that got the perfect score, keep up the good work. For the other, if your score is good, keep up the good work. If not, just try to work harder. Okay? As long as you keep in touch. If you're going to have a problem, email me. Because what happened, if somebody got problem, they stop and I was not able to know it, then that's where the problem happens. So are we clear on that? Before we continue, yeah, some of them know me already. Okay, so I always have the same thing that we have the first time you took the course with me. So I just want to make sure that everybody's on the same page. Okay, so this week I will open the chapter 3 quizzes from what we call Thursday to Friday. And based on the records that I have, okay, uh, almost all of you are doing it at the what 11th hour. Sorry, somebody is disturbing me here because she has an online during Wednesday. Okay, now we're going to expand our calculation. So what we have so far here are chemical formula. What happened if we have a chemical equation? So remember, we have what? The mole going to the mass, going to the number of particles. Now, what happened if we have a chemical equation? We just expand this one. So we just assign, let's say, this is the mole of A, the mass of A, the number of particle of A compound or element or whatever substance, and this is the mole of B, the mass of B, and the number of particles of B. So where will the connection comes between the two? Because we know these are connected, and this is definitely connected. But how are you going to connect A and B? Anyone? In which of the three are we going to connect the two substance? Yep. The quiz will open on Thursday and until Friday. So both quizzes are going to be open on Thursday and up to Friday. Okay. So where are we going to connect the two? Oops. This is where we're going to connect the two. And what will connect the two? The chemical equation. The coefficient of the balanced chemical equation. So the way that we're going to have here in stoichiometry, this is just the calculation of the quantities of reactants and product involved in a chemical reaction. So what we have done so far are all chemical formula. But what we're going to do right now is we relate one chemical formula with another that is in a given equation. So the coefficients of the balanced chemical equation can be interpreted in two ways: molecular level and molar level. So when you say molecular level, that's the number of molecules. When you say molar level, that's the number of moles. Which one you're going to use depends on your needs. So if we're going to look at the relationship that we have, so this thing here, to find the amount of B, whether it's a reactant or product, given the amount of A, which is another reactant or product, you're going to convert grams of A to moles of A. using the molar mass, like this. You're going to convert the moles of A to moles of B using the coefficient. So if we're going to look at this thing here, this is just this portion. But you can extend it to the number of particle. Okay? So this is what stoichiometry is all about. So what's the first thing that you need to know whenever you're dealing with stoichiometry? Make sure the equation is balanced. Don't assume that it is balanced. Most likely some of them are not balanced. Okay? So for instance here, you're given propane, and it says here, the gas burns according to the following equation. Propane reacting with 5 moles of oxygen, producing 3 moles of carbon dioxide and 4 moles of water. Now you are asked how many grams of CO2 are produced when 20 grams of propane is burned. So what does it mean? You have a 20 grams of this, you are asked how many grams of this. So the pathway that you have could be the mass of C3H8 going to the mass of CO2. So always have this starting point and the final destination. That's how you solve problems in science. Where do we start? Where do we end up? And what are the paths that you're going to take to reach your destination? So I can start with the 20 grams. So what will I do? I need to determine the molar mass of this, because for every 1 mole of C3H8, that corresponds to what? So by this time, you should be able to calculate the molar mass on your mind. So 3 times 12.01 plus 8 times 1.008. So that will give me around 44.0946. So I just want to make sure. 12.01 times 3, that's 36.3 plus 8 times 1008. I have a 44.05. So how do we get this one? So 3 and then H. Oops. So that's 3 times 12.01, and then you have here H. That H times 1.008. So if you're going to do this, that's 36.3, and this one is 8.0064, giving you 44.094. Okay? And then what's next? You have to determine the relationship in terms of the coefficient. So for every 1 mole of C3H8, you have 3 moles of CO2. And then you also need to get the molar mass of CO2. So for every 1 mole of CO2, you have 1, 2 times 12.01 times 16. So you have 12.01 times 32, you have 44.01. So what we're going to do, cancel the one that can be canceled, leaving you with the one that is being asked. Analyze. So 20 times 44.09 divided by times 3 times 44.01. So you have here 59.88, since we only have 3 significant figures as the starting point. So we can do it like this. This may be challenging, but if you know what you're doing, I think you'll be fine. Question. Now we can utilize the same problem, but this time ask different question. In the next slide, you are asked, instead of carbon dioxide, you are asked 20 grams of propane will produce how many grams of oxygen? So you will start the same thing as this one. Okay, I have the 20 grams, just like the same earlier, C3H8, and then for every 1 mole of C3H8, I divide it with the molar mass of C3H8, which we found to be 44.094. And then for every 1 mole of C3H8, you have to find what is the equivalent in the oxygen. So that's 5 moles oxygen. And then for every 1 mole of oxygen, what's the mass of your oxygen? So that's just 32, right? And then if you're going to look at these grams, moles of propane, and then moles of oxygen, leaving you the grams of the oxygen, which if you answered would be around 72.6. Please check. Analyze. Let's just have a water break. There you go. So question so far. Okay, there's someone. 20 divided by 44.094 times 5 times 32. It's around 72.5722. Okay, so I want you to double check. So this divided by this times this times this. And that's what it gives me. Oh, I cannot show you the calculator. It's 72.57. So you have to be very careful because I told you, okay, uh, if you do the calculation, any wrong calculation, it's in one of the choices. That's why I don't know if I'm happy that you finished the quiz in less than 10 minutes. Because I look at some of the what we call quizzes that you have, I can see how much time did you spend. Okay, so I would suggest utilize the time given to you until you're sure that you are correct in the answer. Okay. Now, synonymous to this one is the concept of the limiting reactant. So if we go back to this problem here, what happened, let's say if you have 20 grams of this and then 20 grams of this. So are all of them going to react? Usually what happened, only one of them will utilize the whole 20 grams while the other one, okay, will just react in the amount that is lower, or we could say less than the 20 gram. Because we have this concept of a limiting reactant. Okay, so when we have a limiting reactant, this is the reactant that is entirely consumed when the reaction goes to completion. And this is the reactant that will dictate how much of the products will form, okay, and how much of the other reactant that's going to utilize. So any problem giving the starting amount for more than one reactant, that is a limiting reactant problem. In the problem that we have here, this is not a limiting reactant problem. We could say here, okay, this is not a limiting reactant problem. Now, the limiting reactant problem is you're given the amount of more than one reactant, and you will ask which will serve as the limiting reactant. Okay, so if we're going to look at the concept of this limiting reactant, try to look it in this way. So how do you pronounce this? Esmore? Okay, so one small you have here, it's made up of 2 cracker squares, 1 marshmallow, and 3 chocolate squares. So if you're going to have, let's say, 2CQ, 2MM, okay, and we could say 6CH, how many of these you're going to form? So, how many? If you have these ingredients, how many of a small that you're going to form? You're only going to form what? 1. These are all used up. At the end, you have an excess of 1 marshmallow, and at the end, you have an excess of 3 chocolate squares. So that's the concept of the limiting reactant. Your product will only go as how your limiting reactant dictates it out to, until what extent it can go. Okay, so all the amounts that are produced and reacted are determined by your limiting reactant. Now the question, how do we determine the limiting reactant? So they said here, you use the given amount to calculate the amount of the product produced. And usually the limiting reactant will be the one that produces the lesser or least amount of the product. Okay. So whenever you're given the amount of both reactants, what you're going to do is you react it and determine how much product that is going to form. And the one that is less, that's the one that you're going to what we call determine. Okay, so let's try. So if you have a magnesium metal that is used to prepare zirconium metal, which is used to make the container for nuclear fuel. So you have this reaction. Now you are asked, how many moles of zirconium metal can be produced from a reaction between a mixture containing 0.2 moles of zirconium chloride and zero point 0.5 moles of magnesium. So which is the limiting reactant here? Because that's the one that will determine the answer here. So if you're going to look at here, if I use this as a limiting reactant, I have to determine how much zirconium metals will I produce. So what will I do? I'm going to use the stoichiometric ratio, the balanced chemical equation ratio. So for every 1 mole of my zirconium Cl4, I have 1 mole of zirconium metal. And that will just give me what? 0.20 moles of zirconium. And then I have to do the same thing with magnesium. And I look at it, for every 1 mole of zirconium, I need 2 moles of magnesium. So if I have this here, this will be only equals to 0.25. So which is the limiting reactant? Anyone? Type it in the chat. Which is the limiting reactant between the two? Okay, how about the others? So the limiting reactant here is the one that produces the less amount. So in this case, you produce only 0.2 moles of your zirconium when you use zirconium chloride. So this is your limiting reactant. And the answer to your question is this one. Okay? Now, what if we use it here in this problem? Let's say, okay, just let's say, if we're going to restate this one, how many grams of CO2 are produced, okay, when you use or when you have 20 grams of propene and 20 grams of oxygen. Now I try to simplify this because we already solved how many grams of CO2 we produce when we have propene, and that's 59.9 grams per carbon dioxide. So all we need to do now is solve how many grams of CO2 are produced when we have 20 grams of oxygen. So I'm just going to replace this with oxygen. And if you're going to look at the oxygen here, so for every 5 moles of oxygen, you have 3 moles of CO2. And for every 1 mole of CO2, you have 44.01 grams of CO2. So how many grams of CO2 that we have here? So 20, because this is a good problem in grams. The one that we have initially is just moles. That's a very easy one. So what if the one in the chapter quiz is in grams? So you have 20 grams divided by 32 times 3 divided by 5 times 44.01. So you end up with 16.5. Now, which do you think is the limiting reactant between propane and oxygen if both of them has 20 grams? Anyone? So 20 grams C3H8 versus 20 grams of the oxygen, which is the limiting? Hello? Still there? So what is the answer? If I have 20 grams of propane and 20 grams of oxygen, which of the two is the limiting reactant? One produced 16.5 grams of carbon dioxide from 20 grams of oxygen, and the other one produced 59.9 grams of carbon dioxide from 20 grams of propane. So which is the limiting reactant? What shall we say? The one that produced the less amount, that's the limiting reactant. So between the two, okay, the 20 grams of oxygen is the one that is the limiting reactant. So I want you to watch again the video if it's still not clear to you about this limiting reactant concept. Okay, so it's just using the formula and stoichiometry. So given the reactant, you determine how much product you're going to produce. And since you're given both of the reactants, so you have to do calculations on both of them. And the one that will give you the less amount of product, that is the limiting reactant. Okay? Now, what do you call, if this is the limiting reactant, what do you call magnesium? So if you have a limiting reactant, okay, so that's the one that used up. The other reactant is what we call the excess reactant. Now, you may ask yourself, how much of the magnesium remain unreacted? So how are we going to solve that problem? Okay, so we can go from the zirconium chloride because that's your limiting reactant. And what we're going to do, we need to determine how much of your excess reactant was used. So we can determine how much was left unreacted. So 0.2 moles of zirconium chloride. So for every 1 mole of zirconium chloride, you have 2 moles of magnesium. So what does it mean? If you have 0.2 moles of zirconium chloride, you're going to need 0.40 moles of magnesium. And the question, do you have that 0.40 moles? The answer is yes. In fact, I have 0.5. So in this case, if 0.4 moles of my magnesium reacted with zirconium chloride, I have 0.1 mole of magnesium that remain unreacted. That's why it is excess. You have an excess of 0.1 mole magnesium that didn't react. Okay? Analyze. So let's try to solve another problem. This might be, we could say, complicated, but if you just follow what we're doing step by step, okay, you should be okay. If it's not clear to you the first time around, you can look at the video again and see. So this is another example of a limiting reactant problem. So you have here urea used as a nitrogen fertilizer manufactured from ammonia and carbon dioxide at high pressure and temperature. So you have this reaction, urea, 2 moles of urea reacting with 1 mole of carbon dioxide to produce 2 moles of ammonia reacting with 1 mole of carbon dioxide to produce urea and water. Now, you are asked here, if you have 10 grams of each of these reactants, okay, what will be the maximum quantity in grams of urea that can be obtained? And how many grams of the excess reactants are left at the end of the reaction? So maybe the best way for us to solve this problem is to solve how much ammonia is produced if we use this as the limiting reactant and if we use this as the limiting reactant. That's why I put here an extra page. So I can start with maybe the ammonia here. And then on the other side, I can use the 10 grams of CO2. So the same thing that we did for every 1 mole of ammonia. So this time you should be able to get the molar mass right away. Okay, I have around 17.072 or 24. And then based on the reaction, for every 2 moles of ammonia, I have 1 moles of urea. And for every 1 moles of urea, the corresponding molar mass is given as 60.06 gram CH4 N2O. So I can determine here the grams of CH4 N2O that I have. So do the same thing here, but this time it's carbon dioxide. So I have 1 mole of CO2, which is 44.01 grams of CO2. And then you have here, based on the reaction, for every 1 mole of carbon dioxide, you have 1 mole urea. And then you have here, for every 1 mole of urea, you have 60.6 grams of CH4 N2O. So where did I get the 60.6 gram? That's just the molar mass of urea, and try to get the corresponding urea that you have. So try to solve. So based on my calculation here, I get around 17.6 here, and I get around 13.8 here. So which is the limiting reactant?
CO2.
Hmm? The
CO2.
CO2. Okay. Now we are already what we call solve the problem. What is the maximum quantity of urea that can be obtained? Now you may ask, why is this the one that we chose, but this is less than that one? Well, that's the thing. Okay, we determine which is the limiting reactant, and the limiting reactant is the one that produces less amount of product. So between the two, only the carbon dioxide that will reacted, all 10 grams of it. For the NH3, not all of the NH3 will react, because the next question that we have, how many grams of the excess reactants are left at the end of the reaction? So if we're going to look at this, okay, we need to determine, okay, if we use this ammonia, the CO2, how much ammonia do we need to use? Okay, because that's the question that we have. So we can start doing that thing again, but this time we have to determine how much of the ammonia are we going to utilize. So you're going to look at the stoichiometric ratio here. For 1 mole of CO2, you have 2 moles of NH3. And for every 1 mole of NH3, you have the molar mass of NH3, which is 17.024 grams of NH3. And if you're going to get the thing here, so the one that is left there is the ammonia. And that's around 7.7. So this is the amount that reacted with the 10 grams of carbon dioxide. And if you want to determine the excess, all we need to do, subtract the 10 grams with 7.73, which tells you that there's around 2.3 grams of ammonia that remains unreacted. Analyze. We're almost done in the chapter. You want a break? There's only one more, but I'm okay with the break. 10 minutes? Okay, let's have a 10-minute break.
Maybe you could go drink some water or go to the bathroom.
Oh, no, it's okay. We finish it, Talina?
10-minute break.
Okay, so the last concept that we have is just what we call the one that you're going to use in your organic chemistry. So when you do organic chemistry 2 there, you will be asked the theoretical yield, the actual yield in your experiment. So when we say theoretical yield, that's the maximum amount of a product that can be obtained by a reaction from the given amounts of reactant. So this is the calculated amount. Now the actual yield, that's the amount of product that is actually obtained. Okay. Now you may ask, why do we need to determine the theoretical yield? So the theoretical yield, that's the maximum amount that you can produce. Okay. So what happened in this experiment that we have, the 13.8 grams of urea, that is your theoretical yield. Okay, that's the maximum amount that you can produce. But the problem is there's no such thing as 100% efficiency, right? So what happened is you always calculate the actual yield. It's okay if it's 100% yield, but what happen in most reaction, there's always side reaction. So you don't get the maximum yield. You don't get the amount that is predicted by the theoretical yield. So if you're going to look at the difference between the actual and the theoretical yield, so you divide actual over the theoretical yield, you get the percentage yield. Okay? Now, why do you say this is useful? Why did I say this is useful in your Orgo 2? In your Orgo 2, you're going to have an experiment. You have the amount of the starting material, and you are asked to calculate for the theoretical yield. Okay, so if this reaction that you have here, okay, we have 10 grams of carbon dioxide. So the theoretical yield, if there's a 100% yield here, the amount is 13.8 grams. But when you do the experiment and you found out, hey, I only get 10 grams. So you're going to determine the percent yield. So that will be 10 grams divided by the theoretical yield. Okay. Maybe it's just like business. You get, okay, this is the maximum that you can get, but what you usually get is less than that. And sometimes it's even lost, a negative yield. You end up spending more than getting money out of the business that you try to propose. So I use the same example here. So as I said, 10 grams of ammonia, 10 grams of carbon dioxide, the limiting reactant is CO2. So this is just confirming the problem that we have earlier. And its theoretical yield is 13.6 grams of urea. So when this reaction was carried out, you have 9.3 grams of urea. So what is the percent yield? So you just have to use this one. So 9.3 divided by 13.6 times 100 will give you what? 68. So question. Now, the next chapter that we have, chapter 4, I think we're going to have a break in between on that because that's the longest among all chapters. But after that, I think the 7 and 8, no, 6 and 7, no, yeah, 7 and 8. That's the one that is a little bit shorter. In fact, in 7, we might go faster. So the Wednesday that we have next week might be, we don't finish with one chapter. We go ahead with the next chapter after that. Because on 21, I have to attend something. So we will not meet the whole time. So maybe we'll talk about it next meeting. Because the kid here that's always pestering me, he had his moving up ceremony. And I think as a father, I need to be there. Okay? So question. So I'm going to make the chapter quiz available tomorrow until Friday. Okay? If ever I wasn't able to do it today, some of you can remind me just like last week, but usually I have it in the calendar. So I'm really going to change the deadline, the due date for the what we call chapter 3. And for those students who missed the chapter 2, remind me also to open it, but you can only do it this week. Next week, if you miss it, but it is already a Thursday, Friday set up, then it's going to be a problem. Okay? So the lab, I might grade the what we call the lab reports for the second one. It's quite long, so it might take me a while. I have to look at your Excel thing there. Okay, but I try to make it available by maybe the weekend, even the experiment 3 that is due today. So question? Before I call it a week for me, but you still have your quizzes. Okay, the lab and the lec.
I have a question. The quizzes that we recently did, could we see how we did on them?
I make them available already, but by the end of the week, you will see which one you end up with wrong answer.
Okay, thank you.
Okay, because I didn't make available, let's say one of them, because some of the your classmates will still take it because you might need them in your final exam. Okay, but this is I can tell you the questions that you got, uh, it's random sequence. So the thing is, some of you may have two, four questions that are the same, but I would say no two students will have the same set of questions. Okay? Because it's all about the principle. If it's a calculation, it's all about the numbers that's changing there. Any more question? So if you really have some, hard time, just let me know. Okay? I'm more than willing to help you. Because if you don't let me know, I'm assume everything is okay. That's the problem. As they said, don't what we call use the word assume, because if you spell it out, you know what I mean. Okay. So for me, if ever you don't have any problem, you don't email me, I'm assuming that everything is okay. But I know for some of you it's not okay. But how will I know if you won't tell me? Okay. Are we good? Are we good, everyone? To those who remain here with me? So, Jessica, Andrew, Ariana, Hamsira, Safar, Anya, Fatima, Talina. Who else did I miss? Yeah, I think there's only what? 8 of you that remains. Okay? I'm hoping that the recording helps you. Okay? So, see you Monday.